Welcome to ARVN, Amateur Radio Video News. The program you're about to see is free to watch, courtesy of YouTube. Thanks, YouTube. But it wasn't free to make. ARVN's got a lot of money invested in video equipment like this sweet camera and that editing system back there. And it takes a lot of time to shoot and edit a program like this. So I'm asking you to make a voluntary payment, contribution, whatever you want to call it. Just stop by our website, ARRL.TV, and you'll see a link to make that payment, whatever you think the program is worth to you. I guess you could say that this program is brought to you by you. So thanks for watching and enjoy the show.
I'd like to introduce David Rowe, who gets the most traveled award for the DCC from, and I didn't know there was a Southern Australia. For us, Australia is South.
Yeah.
Okay, so David Rowe VK5DGR. And a CODEC2. Now this is something that David's been working on for a couple of years now. This is incredibly exciting to have a low bit rate codec and an open source one at that for use in amateur radio and other applications. Of course, what we would like is something that we can work at HF frequencies. So David's going to tell us about his development there.
Thank you very much, and I'm very happy to be here. My name's David Rowe. I'm from Adelaide, South Australia. I travelled 30.5 hours to get here. Right now is when I usually get up in the morning, so if I fall asleep on you, just give me a little bump. So I'm going to talk about CODEC2. It's an open source speech codec. The target bit rate's 2400 bits per second and below. Applications are digital speech for VHF and HF radio. The idea of CODEC2 is to fill a gap in open source speech codecs beneath 5,000 bits per second. There are a few speech codecs above 5,000 bits per second that are open source. For example, the Speaks codec, which is good for speech, plus a bunch of other music and audio codecs. But nothing much that's open source beneath that 5,000 bits per second. And that's what we really need to get it over a VHF or HF radio channel. It's a work in progress. It's actually been going on for some time. It started as some work I did for postgraduate study. And then a few years ago, Bruce Perens suggested there was a need for an open source codec in the ham world. So I dusted off my thesis and started working on it and turning it into a practical codec for use in ham radio and other applications such as voice over IP. The source code and various speech samples are available from my website, and that's the URL there. Okay, why do we need an open source codec? Well, ham radio is an experimental service. We're used to being able to get into the radios, or these days the software. We want to be able to experiment. We want to understand how it works. We just don't want to have the black box. And we want to be able to modify it and do new exciting things with it. Sometimes things that we never envisaged when we started building the software or the codec. So there's that sort of ham radio ethos that I think is behind the hobby, and we need an open source codec for that. Open source also has some other advantages. It means no license fees. You can use it for free. It also just has a lot of practical aspects. It means if you're building a new system on a different processor, or a Mac versus Windows versus Linux, you can just grab the code, compile it, and include it for free. No one's going to give any problems with license fees. You're not going to have to get hold of a special hardware chip or anything like that. So there's a lot of practical reasons why we want open source. And basically, it also gives you the freedom to run it on, say, a PC or embedded chip. In contrast, proprietary codecs, they come in hardware form. You can buy a chip, which is usually a DSP, with the codec flashed on it, or in some sort of license form. They're difficult to distribute. You can't download a chip from a website. You have to get it shipped to you. Or if there's license fees, there'll be certain ways that they'll make sure the code isn't copied, so you have to manage that in your application. So distribution is difficult. You can't modify a proprietary codec. There's no way you can change the bitrate, change the fault error correction scheme, because it's all locked up. Understanding how they work is actively discouraged. They will try to make sure you can't understand how it works because they're worried about copying it or doing other things. In fact, it may be illegal to modify the codec, which is sort of the opposite of what we like doing, modifying and playing with things. And the license may explicitly make it illegal to modify that software. Okay, so who am I? I'm from Adelaide, South Australia. Was first licensed over 30 years ago. I really got my start in my career through ham radio. So for me, this is a way to give something back. I've now developed some skills in the speech coding area which are needed, and I'd like to put something back into the hobby. I've had 20 years experience in speech coding. Back in the late 1980s, we got hold of some of the first digital signal processors, which were a single chip that in particular had fast hardware multipliers. In those days, fast was 10 to 20 million operations a second. And suddenly it became possible to run low bitrate speech codecs in real time. Until the late 1980s, you really had to just run them in simulation form. Back in those days, it might take an hour or so to process a minute of speech on an early PC. But suddenly we could do it in real time, and I got involved in some of the first real-time speech codecs. In those days, it was for telephone services getting more channels of speech down digital telephone lines. Now I work full-time on open source software, in particular software and hardware for communications in the developing world, and work on projects like this part-time. Okay, so in a digital voice radio system, I'm mainly concerned with the codec and encoder. There's other blocks, like hardware that we use to sample the signal. Usually there's some sort of forward error correction, which will take the bit stream from the codec, protect some or all of the bits using redundant information. So they'll add bits or add bit rate to the bit stream. Then we'll have some sort of modulator, feed it into a HF or VHF radio, and on the other side we have a demodulator. That'll convert it, give you a bit stream that will then correct bit errors with some forward error correction. That'll be fed into the speech decoder, which will take the output will be fed to the speaker. So the sort of signal rates we're talking here is we might be sampling the speech at 8,000 samples a second, 16-bit integer samples, and out of the codec we'll have something like 2,000 bits per second, and that'll flow over the channel, come back here at 2,000 bits per second, and we'll have an output at 8,000 samples a second, 16-bit samples. Now, this is the classic signal flow diagram, and what we're doing at this point is we're simply treating the digitized speech as a bit stream, just like it could be data, it could be an image or something else. I believe that's not quite the right way to treat it. Speech is very special digital data. It doesn't matter sometimes if you've got certain bit errors in the decoded speech signal. Normally, for data transmission, if we have unrecoverable errors, if we have, say, a checksum error in our packet, we throw that packet away and ask for another one. It's got to be perfect or the data's no good. That's not so with speech. You can get by with 5, sometimes 10% bit errors and still decode the speech signal into something that's intelligible. So down the track, I'd like to treat these blocks, rather than sort of discrete items, as something that we consider together. And I believe there's some big advantages we can make in the effectiveness of the communication system by treating these together, rather than just say treating this as a bit stream that's got to be perfectly protected, etc. I'll talk a little bit more about that later on. Okay, patents and speech codecs. When you look into this, you find that there's a few little tricks these guys are using. Most proprietary speech codecs borrow most of their DSP code from the public domain. They're using the same sort of algorithms that are just available in any textbook. Something like 95% of the algorithms are simply public domain algorithms. But what they've done is, with about 5% of the algorithms, they've come up with something clever or novel that improves the speech codec significantly, and they've patented that and used it to lock the codec down. And that means they can charge license fees, create a good business, but it's a disadvantage to people who want to experiment and use the codec for other things. So it's not like these guys invented speech codecs. It's not like they invented the only way to do speech coding. There's always many different ways to do it, and what we need to do is simply work around those 5% that's locked up and make the whole thing public domain rather than just 95% of it. So it is possible to get an equivalent sounding speech codec, the performance, what it sounds like, its robustness to errors, its performance in background noise. It's possible to develop an equivalent codec without the patents and the encumbrances that brings. It's probably not possible to make it compatible with one of the patented codecs. So it's not going to be bit string compatible, and that's a bit of a disadvantage, but it is possible to get similar performance. So what is speech coding? The trick to speech coding is what can we throw away? We take the input speech samples and we want to convert it to something like 2,000 bits per second. But speech has the property that the signal has a lot of redundancy in it. In particular, speech has a lot more redundancy than, say, a general purpose audio signal like music or some other sort of audio signal. So because there's a lot of redundancy, we can throw a lot of information away and still code the speech signal in a way that it's useful. The way we define what is useful is intelligibility. That's the ability to understand what's being said and to get a good sort of understanding of the different words that are being said. And there's also the naturalness or speaker recognition. Does the speech that comes out of the speech coder sound like a robot, or is it natural sounding or reasonably the same as the person who started talking into the speech codec? So they're the two things we try to work on with the speech codec, and everything else we'd like to throw away to minimise the bit rate. Now, typical speech signals start at 8,000 bits per second, say 16 or 8 bits. Say 64 kilobits a second is what you'd get out of an ARRL speech codec, which you might be sampling the audio signal with. The lower limit is something like 50 bits per second for human speech. That's the information rate of what I'm talking about at the moment. If you just converted my voice to a robotic voice and it was just the same words coming out, it's around about 50 bits per second. So that's the lower limit. Anything in between, the better the speech codec is, the better the speech will sound, the more intelligible it will be. For low bitrate speech codecs, beneath around 5,000 bits per second, we use something called model-based speech coding. So rather than taking the waveform and just quantizing it, we actually look at chunks of the waveform, might be 20 or 40 milliseconds of the waveform, and we try to fit a model, for example, a speech production model. Our vocal tracts, our throat, our mouth, can be modelled as a filter, just like the sort of filter you'd use on the end of a transmitter for filtering. It can be modelled as a 10-pole digital filter. So instead of sending the waveform, you can send those model parameters for that filter. Just like sending the specs that define any sort of analog filter, you can send parameters that define a digital filter that models the vocal tract at any point in time. As we talk and articulate the sounds, the parameters of that filter change over time. It's time varying. So what we tend to do then is update the model parameters every 20 or 30 or 40 milliseconds as the speech sounds are articulated. So that's called model-based speech coding, as distinct from waveform-based speech coding, which might be quantizing the waveform at different levels. And we tend to use model-based speech coding for the lower bit rate. So an example of a model parameter is the pitch of the human voice. That tends to range over, say, 50 to 500 hertz. 50 hertz would be your deep male baritone, 500 hertz might be a young child. And as we articulate the sounds, the pitch changes, it goes up and down. It's used to convey often emotion as the pitch raises or lowers, or in some languages it's used to convey the intelligibility, such as tonal languages. The pitch is one parameter that can be quantized to around about 7 bits of resolution, and we need to update it something like about once every 20 milliseconds. So for that particular model parameter, if it's 7 bits updated every 20 milliseconds, we need around 350 bits per second to represent the pitch in that sort of speech codec. Pitch is another good example of a model parameter that has a lot of correlation from frame to frame or redundancy. As I talk, my pitch is not going to change quickly. It's going to change over the duration of a sentence. So what that means is that this 7-bit number I'm sending might only vary by a few bits. It might be 64 one frame, 65 on the next frame. So that indicates that you might be wasting bits by sending all those 7 bits. It might be more efficient to send a delta or a change from frame to frame. And you can see then if you're just sending a change with a couple of bits, you can lower the bit rate required to send that parameter over the channel. The disadvantage is if you get a bit error, coding the change, the bit error might accumulate over time, so it might not be as robust to bit errors. So that's just a little example of one model in a model-based speech coder, and that's an example of one model parameter, sorry. Now, the entire speech model we use for CODEC2 is called sinusoidal speech coding, and I've got a few figure-based explanations here that show how it works. This is a plot of a short period of time. It's 300 samples. That's about 40 milliseconds of speech when sampled at 8 kilohertz. This is female speech, the start of a word. You can see the amplitude scaling up over the frame. You can also see this regularity in the waveform. It seems to be roughly repeating itself. that repetition rate just happens to match the pitch of the voice. So it's or the pitch period or the pitch frequency, or just the pitch for short. In this case, it's around 35 samples, 4.4 milliseconds is the pitch period, or around 230 hertz in this particular frame. Of course, the pitch does vary a little bit over the frame, but we just approximate it by saying it's 35 samples for this particular frame. So what we've got is this periodicity, the signal repeating itself every pitch period, and that's a time domain frame of about 40 milliseconds. So let's look at that same signal in the frequency domain. So any signal that is periodic in the time domain that repeats itself will also be periodic in the frequency domain. So what we're seeing here is these spikes here, they represent harmonics of the fundamental frequency. And they're spaced at the pitch period, or the pitch, which is 230 hertz. So the first one's 230, second one's 460, etc. And you can see it's got this spiky appearance of harmonics that stretch all the way out to the aliasing frequency. So what we can say is that the speech is made up by a bunch of sine waves. Each one of these sine waves represents a harmonic of the fundamental. So the idea of a sinusoidal speech coder is we say the model we use is a bank of sine waves that generates the speech signal. The model's not perfect. There's some points like here where it doesn't look like a perfect sine wave. It's not a perfect spike. Also, because the pitch is changing across the frame, some of the higher frequency ones are wider because the frequency wasn't constant of that harmonic. It's smeared over time. But the model ends up to be reasonably good. It gives you quite high quality speech. So we're modelling the speech as a bank of sine waves. There's another parameter here. Another thing we can see here is that each adjacent harmonic, each adjacent sine wave, tends to be related in amplitude to the one before. For instance, these ones are fairly closely related in amplitude. Because they're closely related, we can use that to an advantage later on in coding them. So one of the parameters we use for this sinusoidal speech coding is the amplitude of the harmonic, and the red line is a plot of each of the amplitude of these harmonics that we've estimated from the incoming signal. So the model we have for speech production here is a bank of sine wave oscillators. Each one has an independent amplitude, phase and frequency. The amplitudes, as I said, are correlated a little bit over the spectrum. Adjacent harmonics tend to have roughly similar amplitudes. The frequencies are harmonically related. So all we need to know is the frequency of the first one, and the frequency of the rest of them will be a multiple of them. So the frequency is easy to work out. They all have an individual phase as well. However, phase isn't particularly important for speech. We can make the speech quite intelligible just by estimating the phase and throwing that away. So what we tend to do is we worry in particular about the frequency and the amplitude, and the phase we tend to throw away and synthesize that at the decoder using a rule-based approach. I'll talk a little bit more about that later. But the most important parameters are the amplitude and the frequency. And so if you sum them together, this bank of sine wave oscillators, you can reconstruct something that sounds fairly close to the original speech. Now, as I said, the amplitudes, sine wave amplitudes, are quite important for the one of the most important parameters for the codec. They do tend to have similar amplitudes, which leads to coding efficiencies. We use something called LPC, or linear predictive coding, to represent the amplitudes in this codec. Now, the linear predictive coding is similar to that digital filter I mentioned previously. We can model the vocal tract as a digital filter. So what happens with linear predictive coding is you can look at a block of speech and you can run a little program on it, and it estimates the digital filter parameters for that frame of speech, and then they get updated every now and again. Now, one of the problems with this model is that the number of harmonics is time varying. Because the pitch varies, that means a different number. If the pitch varies, you'll get a different number of harmonics across this frame. If the pitch is 400 hertz, you might only have 10. If it's 50 hertz, you might have 40 or 50 harmonics across the frame. That means we have a time-varying number of amplitudes that we have to encode. That's a problem because we want to keep the bit rate constant. We can't use more bits if the pitch changes. So the advantage of this linear predictive coding is it has a fixed number of parameters that represent this digital filter. That gives us an envelope, which I'll show you in a moment, that approximates the amplitudes. And given that LPC envelope, we can then sample that at the decoder to recover the amplitudes. So this will all become a bit clearer with this plot. This is another frame of input speech. The red line are the original amplitudes of each sine wave that we sampled. And what we do is we fit this LPC model, this digital filter, and that's the aqua line. I apologise if that's a bit hard to see from the back, but there's a gentle aqua line going here that's like an envelope that tracks the peaks of the harmonics. That is the LPC model that's represented by 10 coefficients, fixed number of coefficients that get sent to the decoder. From that LPC model, we can then sample the harmonic amplitudes again, and that's the green line there, the bright green line. Now there's some errors between the green line and the red line. It's not perfect. That's plotted down here on the purple. You can see it's not perfect. There's a bit of distortion, but it turns out that it still sounds okay. Even though there's quite a bit of an error there, we don't really notice that. The energy of the signals around it overcomes that energy, and it sounds okay. So that's how we do the amplitude modelling in CODEC2 using one of these LPC models. This is a block diagram of the CODEC2 encoder. The input signal comes in here at 8 kilohertz. We then have various algorithms that we pass through it to estimate various parameters of the speech coding model. The first one is a pitch estimator. We have to try and estimate the pitch of the incoming speech. That can be quite difficult, especially when the pitch is changing quickly or there's background noise. And the problem with any of these models is they break down under certain circumstances. So to make the pitch estimator robust is quite difficult, and quite a lot of work has gone into that. We then use an FFT to convert the signal into the frequency domain, and we do something called voicing estimation. Speech, for the purpose of model-based coders, speech can be grouped into voiced and unvoiced sounds. Voiced sounds are sounds like vowels, and unvoiced sounds are sounds like consonants. When we're synthesizing voice sounds, we use the sinusoidal model, but when we're doing unvoiced sounds, it's more accurate to treat the signal as noise-based. And so we have some sort of voicing estimator that's a single bit that really just classifies the speech as, say, a vowel or a consonant. And then we have the LPC analysis that I mentioned previously, that's modelling the spectral amplitudes, or the magnitude of each sine wave. When we want to transmit it over the channel, we convert the LPCs into something else called LSPs, line spectrum pairs. They're just an equivalent parameter set that happens to be easier to transmit over the channel. It requires less bits. I haven't got into the maths required for that, but suffice to say it's just a better way to transmit over the channel that's more robust to quantisation. We also quantise the energy of each frame to about 5 bits using a log quantiser. And that's just really how loud the signal is on that particular frame. As I showed before, the LPC analysis can make some errors, so I've also got a correction bit that I transmit in some versions of the codec, which just helps low frequency performance of the LPC model. And that gives us a quantised bit stream that we send to the channel. This is the bit allocation of the current version of the codec, which is running at around 2500 bits per second. We have 20 millisecond frames, so each one of the parameters is updated every 20 milliseconds, with the exception of voicing, which is updated every 10 milliseconds, the voicing bit, which is that consonant or vowel bit. Now, you can see that by far what consumes most of the bits is the spectral amplitudes. That's one of the most important parameters, but it's also one where there's the most capacity to reducing the bit rate of the codec. If we can work out ways to code that more efficiently, say 20 bits a frame or less, we can get the bit rate of the codec right down. As I indicated, some of these other parameters, such as pitch and energy, are also highly correlated. They're very similar from frame to frame. So if we can work out more efficient ways to code these, we can also push the bit rate right down. So there's many strategies we can use to get the bit rate down from here. This is just a starting point. So the quantized bit stream gets fed to the decoder. We recover from the LSPs the LPC model, which was that general that envelope I was showing you on the plot before. We then recover the harmonic amplitudes and feed them into the synthesis stage. As I said, in this model, the sinusoidal model, we need the phase of each harmonic to synthesize it. We don't transmit the phases because they take too many bits, So instead we synthesize them using a rule-based approach. An input to that is the voicing bit. If the speech is voiced, like a vowel, we know the phases are continuous from frame to frame. If the speech is a consonant like noise, we randomise the phases, and that constructs a noise-like signal. So we have a phase synthesis algorithm there. The post filter is to make the codec work better for speech signals with background noise. One of the problems with low bitrate speech codecs is they're optimised for speech signals only. That's how we get the bitrate down. They won't code general purpose audio signals like music or various other things. Because they're so tightly optimised to get the bitrate down, they don't tend to work very well on non-speech signals like, say, background noise. So we have to take special steps in the codec to treat background noise and make it work well. And that can be a real problem if you're, say, driving along in a car, motor noise, wind noise, things like that, a siren for emergency services. What can happen with these non-speech signals is two things. The first is they may sound bad when they go through the codec in an annoying way, or they may cause the codec to break. So it'll know if you mix the input speech with the background noise, you might not be able to hear the speech go through the codec anymore. So to deal with background noise a little bit better, I've introduced a post filter, which tends to estimate the background noise level as it goes along and do some sensible things with it and cause the codec not to break down too badly. That's still a work in progress, but that's something that we're trying to address with the post filter. At the output of that, we use an inverse FFT, which takes all those sine waves, and using an FFT is just an efficient way to generate all the sine waves rather than having, say, 50 sine wave oscillators running in software. It's more efficient to put 50 lines in an FFT and then do an inverse to reconstruct the signal. We use something called an overlap add algorithm that takes the block, every 20 millisecond blocks, and concatenates them into one smooth, continuous signal, and you get your output speech again. Okay, I've got some samples I'd like to play that demonstrate some of the pros and cons of speech coding and where they can break down. The first one is just a standard male speaker that I use for a lot of my testing. I'll be playing the original signal. I'll be playing the signal through an AMBE codec that's used for D-Star, running at a similar bit rate, through CODEC2, and then through CODEC2. And then I think also through LPC10, which is an older standard vocoder. The next set of samples, I would like to demonstrate speaker dependence. This is a sample that works well on the AMBE coder, but not too well on CODEC2. What tends to happen is with speech codecs is you might find one speaker sounds really good on it, another one doesn't. They don't, just because it works on one doesn't mean it's going to work on the others. Because I'm doing this as an open source codec and I've published the source code, I get people from all over the world downloading it, trying it, and they send me in a sample saying, hey, it broke on this or it works really well on this. And that's one of the advantages of open source development. I'm getting all these people sending in samples, doing strange things with the codec that I never would have dreamed, but it helps me develop the codec and trap corner cases. So it's a really, open source development has a lot of power to it compared to doing this as in a lab for secret, so I can put patents on it. I get all this input from other people that helps me develop the codec faster and more efficiently. I've got another set of samples that indicate background noise and what that does to some codecs. And it's kind of difficult to get the full feel of these samples due to room acoustics. The best way to do this is with headphones or on your own laptop at home. So I'd encourage you to try these same samples, download them yourself and have a listen to them to get a real feel. But we'll have a try here. I've got another microphone I can use. Now I've kind of got to do this backwards too. Oh yes, okay. I think I'll just try it here first of all, see how we go. Okay, so this is the original.
The Navy attacked the big task force.
Oh boy, I'm all backwards here. Hang on, I'm going to have to turn around. Okay, so this is AMBE.
The Navy attacked the big task force.
CODEC2.
The Navy attacked the big task force.
And LPC10.
The Navy attacked the big task force.
So I'll run through them again. Original.
The Navy attacked the big task force.
AMBE.
The Navy attacked the big task force.
Codec 2.
The Navy attacked the big task force.
And LPC 10.
The Navy attacked the big task force.
So we can see there, to my mind, Codec 2 is roughly in the same area as AMBE for that particular sample. There's others that AMBE will beat it and vice versa. LPC 10 is probably a notch below where they are. Now here's a sample that where AMBE is clearly better than Codec 2 that was sent in by a gentleman called Christoph, the original.
Hi, this is Christoph, Oscar November 1 Alpha Romeo Fox.
AMBE.
Hi, this is Christoph, Oscar November 1 Alpha Romeo Fox.
I might just turn that down a little bit. Codec 2.
Hi, this is Christoph, Oscar November 1 Alpha Romeo Fox.
So I'll just play the last two again. AMBE.
Hi, this is Christoph, Oscar November 1 Alpha Romeo Fox. Hi, this is Christoph, Oscar November 1 Alpha Romeo Fox.
I'm not sure how that's playing out to the room, but to me the AMBE sounds a bit better than the Codec 2 one. As I said, these things are kind of hard to discern, and I go nuts listening to these things over again all day. One of the problems with speech coding development, it's kind of hard to get an objective measure. And you go back and listen to the same things a day after and you make the opposite decision. So, it makes development kind of tricky. I've got another example here that's background noise. This is truck noise on top of someone speaking. This is the original.
It's easy to tell the depth of a well.
AMBE.
It's easy to tell the depth of a well.
Codec 2.
It's easy to tell the depth of a well.
And LPC 10.
It's easy to tell the depth of a well.
So there you can see Codec 2 just fell over, LPC 10 fell over with the background noise. That's what you don't want to happen. It's an example of the background noise messing with the codec algorithm. The other two they sound a fair bit worse than I'll play the AMBE and Codec 2 again.
It's easy to tell the depth of a well.
AMBE.
It's easy to tell the depth of a well.
Yeah, Codec 2 is better.
I don't know. Yeah, this is where I get confused. I'd be interested to hear what you say. To me, the Codec 2, the background noise isn't reproduced as faithfully. I can hear some sort of staticky, clicky.
Why do we want to reproduce it?
Well, yeah, you might want to attenuate it. That might be an advantage.
I don't understand why a priori we don't assume we're going to do coherent zone and background noise suppression before we ever do the coding.
That is one approach. Yeah, you can do actually noise suppression before it goes into the codec. Speaks does that.
AMBE reintroduces its own noise in its coding algorithm too, so it has a noise model.
Yes, yeah, for unvoiced speech. Yep.
The thing I notice the most is just the fake bass in AMBE.
Right. Yeah.
The fake bass.
Makes it sound hi-fi.
In Codec 2, how are you getting that noise reintroduced again?
It's easy to tell the depth.
I'm sorry?
In Codec 2, how are you reintroducing the noise?
Well, the noise is always there. It goes into the encoder. What I'm doing is...
Because you're doing the sum of sinusoids.
Yeah. It turns out that if you...
It shouldn't be coming through that well.
Yeah, it turns out if you have enough sinusoids and you randomize the phases, it sounds like noise. An example is if you take an FFT.
Sorry.
An example is if you take an FFT and randomize the phase in all the bins and inverse FFT, you'll get something that sounds a lot like noise. The model, if you have a small number of harmonics, then it doesn't sound very noise-like. But if you have a large number, you can approximate noise quite well with just a bank of sinusoids. This is a summary of prior art. This is kind of important if we don't want to get sued when we use it. I did a lot of this codec developed from work that I did in the 1990s, so it was based on work from before that. Anything past that has been stuff I've developed myself. It's possible that some of these algorithms could have been used or developed or patented in parallel to my work. A nice little project one day for this codec would be to someone to do a patent search on everything that's equivalent, just to make sure that we're 100% patent clear. I believe we are. Most of the stuff we're using here is pretty ancient, and if there is something patent incumbent, I'll just come up with another way of doing it and work around it. Further work. I'd like to come up with better phase models and a voicing estimator. That's just to improve the quality. I believe if we come up with a really good phase model, that we can get something like toll quality at 2,000 bits per second, which is a lot lower than current 8,000 bits per second codecs for equivalent quality. Get the bit rate down, initially to 2,400, then to 1,200 bits per second. Better background noise performance, although it's not bad at the moment. I'd like to improve it. Work with some people to introduce FEC and non-redundant error correction. As I said, I don't think it's a really good model to just treat the whole bit stream as a bit stream to be encoded equally with FEC. What happens in these codecs is some bits are more important than others. So you might only want to protect some of the most important bits in the bit stream and leave the rest unprotected. For example, in the pitch,
If some of the bits are more important than the others, that means you haven't done sufficient source coding. You haven't compressed it enough.
That's one way of looking at it, yeah. You could compress it right down to every bit is important to the rest, yeah. There are some reasons why you might not want to do that, though. Anyway, so for example, the most significant bits of the pitch are more important than the least significant. If you make the pitch change from 250 to 500 hertz from frame to frame, it's going to sound a lot more obvious than if it changes from 375 to 400 hertz. So you don't necessarily, not all bits are made equal, and you don't need to protect them all. Remember, in speech, it's okay to have some bit errors. It's not like data. You're not going to throw the whole thing away if you get one bit wrong. There's also something called non-redundant error correction. If you look at some of the parameters that are being received, if, say, the pitch or the energy jumps around wildly from frame to frame, that's usually pretty unlikely. The energy in my speech changes fairly slowly. It's only changing a few dB every 20 milliseconds. So if it jumps 50 dB in one frame, you've probably got a bit error that's been sent, and you can detect and correct that. You can also get some advantages by sending information from the demodulator through to the decoder. If the demodulator says, look, this bit was pretty close to an error threshold, you can take advantage of that information and use it to make an intelligent decision in the decoder. Other work that we really need to do next is just integrate this into a modem and test over radio channels. There's a few people who've done experimental calls, but it'd be great to get this into some sort of laptop implementation that everyone can try. Hook it up over their HF radio. Down the track, we've got to do a fixed point implementation and get it running on a DSP chip so people can put it in embedded devices. At the moment, everything's in floating point, which works okay on PCs, but it's not too good for embedded chips and DSPs. Here's just some sort of random ideas of what we could do with CODEC2. And one of the reasons I'm at this conference is I'd like to get some feedback from you guys on what you'd like to do with it and what you'd like to see. Another question here.
Okay, so I would say the most popular embedded chip in the world right now is the ARRL. It has the neon, and you can continue to do floating point forever. Mm-hmm. I don't see any reason to do anything but floating point, given that we have the ARRL or the neon in it. That's just one comment. The other thing is, what do you believe the actual information rate is on the changing LPC coefficients? So, I mean, just your ballpark guesstimate.
Oh, I think if you had the right coding scheme, down 10, 15 bits per frame.
Yeah, so I'm thinking that there are probably better expressions for the power spectrum than LPC. Like some very good wavelets, I think, might do a better job there, a much better job. And you would drop it from about 50 to about 20 or 25 easily. Yeah. And I think with a little bit of work, it would go further. I believe a wavelet expansion for the power spectrum would do a lot of good.
And do you have any, the mic is, do you have any female examples that you can play?
I do.
On your machine? I would like to hear a female.
Yeah, sure. Sorry, I left that out. I can do one of those. Perhaps I'll just finish this slide, then come back to the female, if that's okay. Another question?
Actually, I was just earlier doing a talk on D-Star, and there's always been a lot of back and forth here with D-Star and the Ambi chip and the proprietary codec and the whole saga there. But one of the things I wanted to talk about at this conference here, or maybe bring up tomorrow, like some other ideas or extrapolations for D-Star. let's just say digital technology, not necessarily D-Star, the ICOM implementation or whatever, is especially when you're talking about things like VHF, UHF radios. One of the first places of interface that we're working with is just the 9600 baud packet port that's available on radios today. One of the other questions I would have then is, instead of going down in bandwidth, a lot of people complain about the audio quality of any of the codecs or whatever, and if we wanted to just work with what is essentially, if you think of it from a packet port perspective, you got a 9600 baud channel. What could you do to have maybe, let's say, a higher fidelity audio stream that could be digitized and then sent out over, VHF, UHF radio? So I'm not really targeting the HF side, but just trying to come up with something where once audio is digitized, it's digitized at the source. It's now data that can be routable, and moved around or whatever.
Yeah, there's quite a few codecs above at that sort of bit rate, like telephony ones, like G729 or Speaks at those rates. It'll do a fine job already if there's no bit errors, well, not many, and it's just a 9600 baud channel. Yeah. So in terms of coding, that problem's been solved.
So do you, or do codec designers tend to create different codecs for different types of languages, like tonal languages?
I've had this been asked once or twice before, but I think it's okay for most languages. The only one I've heard strangely is some of those gods must be crazy type languages with the clicks like and stops. Yeah, but my understanding is most speech coding algorithms operate on tonal, like Asian languages.
We probably don't need to code for the 10 people that need it.
There you go.
In addition to codec efficiencies, what about transmission efficiencies like 80 PCM and things like sending just the difference between the bits and that kind of thing?
Yeah. Well, that's something that could be done for, say, parameters like the pitch and the energy. You could differentially encode them. That has a disadvantage of error propagation. If you get an error in one frame, that error will propagate through, but you can have lossy differential things that will eventually recover from errors.
Yeah, is it possible to pre-code, your voice by just going through, Alpha, Bravo, Charlie sort of sequence, and then set up, the codec for your voice, and then send those parameters ahead of time?
Yeah, it's a good idea. I hadn't really thought of that, but I guess so. Yeah, you could code those things and have them reduced to very small tokens. So I think the next step is to, what I want to find out from you guys is, is this interesting to you? How can you use it? How would you like to use it? What I'm hearing from working with people like Mel is that what we really need is something that can run on HF radio, get the bit rate down around 1400 bits per second, get a bit of PC software so that you can put this on your laptop, hook it up to some headphones and your HF rig, and get into digital voice. But that's what I'd really like to do, get that next step, get it out there, and get people using it and see where we can take this. I'd also, as I said, like to explore novel combinations of the codec, FEC and modulation. One thing we might be able to do is put the more important parameters on an OFDN spectrum with multiple carriers. Might be able to use more energy for the more important parts of the speech signal. The other idea that's been suggested to me is some really low bitrate mode for voice, a little bit like PSK31, something that can push through really bad channels. It might be very poor speech quality, just intelligible, but not very recognizable, but it might get through where no other voice channel can. Maybe in 500 hertz of bandwidth and at very low signal to noise ratios, much better than SSB, usable for contests or when spectrum's very tight. That's the sort of thing we can experiment with, just to give you an idea, when we've got an open source codec that can be changed. So, and another thing I'd like to try is, can we get this to be better than SSB on HF? Better sound quality at less power and less bandwidth. SSB's been around for 30, 40 years in common use. Can we do better now? Thank you.